The ground trembles beneath you, a low thrum echoing from the colossal concrete wall stretching into the distant haze. A trickle of water, then a torrent, plunges from a dizzying height, shattering into mist hundreds of feet below. You stand at the edge of a man-made canyon, watching a leviathan of steel and rock harness the very flow of a continent. Then you look up, and the scale truly hits you, a concrete edifice taller than some skyscrapers, holding back the weight of an inland sea. How do we build structures that reshape geographies, command rivers, or span oceans? How do we carve tunnels through mountains or launch laboratories into orbit? This is not merely a question of brute force, it is about redefining what is possible through ingenuity, persistence, and an unwavering belief in solving the unsolvable. We're going to explore 9 megaprojects that pushed the very limits of human engineering, revealing the astonishing mechanisms that make them work. Number 9, the Golden Gate Bridge. Imagine standing on the rugged cliffs of the Golden Gate Strait in the 1930s. The wind howls, carrying the biting spray of the Pacific, and the swirling currents below are notorious for their treacherous power. To span this formidable 2-mile gap seemed an impossible dream, a challenge met with skepticism and fear of the elements. Yet, engineers envisioned a structure that would not just cross the strait, but dance with it. The challenge wasn't just connecting 2 points, but doing so across an active seismic zone, through constant high winds, and over a depth of water that precluded traditional supports. The trick lay in the bridge's very flexibility. Unlike rigid structures, the Golden Gate Bridge is designed to sway and undulate. Its 2 main cables, each 3 feet thick and composed of 27,572 individual strands of galvanized steel wire, stretch for 7,650 feet, anchored deep into bedrock on either side. These cables drape over towers 746 feet tall, supporting the roadway not by direct compression, but by tension. The entire 4,200-foot main span, along with its approaches, hangs from these cables, distributing the weight and allowing the bridge to absorb the tremendous energy of wind and seismic activity. This suspension design, conceived by Joseph Strauss and Charles Ellis, allows the bridge to deflect laterally by over 20 feet in high winds without catastrophic failure. It doesn't fight the forces of nature, it yields to them, absorbing their energy like a spring. The Golden Gate Bridge, completed in 1937, still carries over 112,000 vehicles every day, a testament to its elegant, resilient design. Number 8, the Millau Viaduct. Now imagine driving across the Tarn Valley in southern France, a verdant chasm that, for centuries, funneled traffic into a bottleneck. The solution proposed was audacious, not just a bridge, but a thread-thin ribbon of roadway floating over 1,000 feet above the valley floor, supported by masts even taller. This wasn't merely about spanning a gap, it was about elevating an entire highway into the clouds, making it invisible from the valley floor and piercing the low-hanging mist. The challenge was unprecedented verticality combined with enormous spans, all while minimizing environmental impact on a protected natural landscape. The innovative mechanism behind the Millau Viaduct is a multi-span cable-stayed design, a stark contrast to the suspension bridge's long main cables. Here, 7 slender concrete piers, the tallest reaching an astonishing 804 feet, support a continuous steel deck. From the top of each pier, a mast extends another 292 feet, forming a total height of 1,125 feet from the deepest point of the valley to the mast tips. From these masts, steel stay cables fan out, directly supporting sections of the deck. This distributed support system allows for a lighter deck structure and provides immense rigidity against wind forces, crucial at such an extreme height. The deck itself was pushed out from both ends of the valley, section by section, like a giant puzzle, guided into place with millimeter precision. Opened in 2004, the Millau Viaduct isn't just a bridge, it's a structural ballet, an aesthetic triumph of lightness over gravity. Number 7, the Palm Jumeirah. Shift your gaze from continental Europe to the shimmering coast of Dubai. Here, where the desert meets the sea, engineers envision not just building on land, but building more land. The scale was dizzying: create an entire archipelago from the seabed, shaped like a palm tree, visible from space, simply to expand the coastline. The challenge was not just moving millions of cubic meters of sand, but creating stable, erosion-resistant landforms in a dynamic marine environment, while also protecting the delicate underwater ecosystems. The core mechanism for the Palm Jumeirah involved hydraulic dredging, a process of sucking sand from the seabed elsewhere and spraying it into place to form the desired shapes. Over 120 million cubic meters of sand, enough to fill 48,000 Olympic-sized swimming pools, were meticulously placed using GPS-guided dredgers. But sand alone would not suffice, it needed protection from the relentless Arabian Gulf currents and waves. This protection came in the form of a 6.5-mile-long breakwater, a crescent-shaped barrier built from 7 million tons of rock, placed in an interlocking pattern to absorb wave energy. The rocks, sourced from 16 different quarries across the UAE, were placed with incredible precision, forming a natural reef that also encourages marine life. The Palm Jumeirah, largely completed by 2006, is a testament to what can be achieved when the very ground beneath our feet is seen not as a given, but as a canvas. Number 6, the Gotthard Base Tunnel. Now, imagine plunging into the heart of the Swiss Alps, not just through them, but under them, burrowing through solid rock for tens of miles. For centuries, the Alps have been a formidable barrier, their peaks forcing railways and roads into slow, winding ascents. The goal of the Gotthard Base Tunnel was to fundamentally bypass this natural obstruction, creating a flat, high-speed rail link directly through the deepest part of the mountains. The challenge was not just the sheer length, but the incredible pressure from thousands of feet of rock above, the intense heat deep within the earth, and the varied, often unstable geology. The genius of the Gotthard Base Tunnel lies in its twin-bore design and the sheer scale of the boring machines. Two parallel tunnels, each 35.5 miles long, were excavated simultaneously. For massive tunnel boring machines, each a self-contained factory over 1,300 feet long, chewed through the rock face. These machines, nicknamed earthworms, featured rotating cutting heads armed with hardened disc cutters, capable of grinding through granite at rates of up to 60 feet per day. The excavated rock, roughly 28 million tons, was then transported out, and the tunnels immediately lined with concrete segments to withstand the immense lithostatic pressure, which could reach up to 1,500 pounds per square inch. The tunnel's operational temperature could reach 46 degrees Celsius, 115 degrees Fahrenheit, due to geothermal heat, requiring extensive cooling systems. Opened in 2016, the Gotthard Base Tunnel reduced travel times across the Alps significantly, demonstrating how we can bend geology to our will. Which of these machines would you least want to be standing next to? Tell me below. Number 5, the Channel Tunnel. Let's move from the Alps to the English Channel, a stretch of water that for millennia has separated Britain from mainland Europe. The dream of a permanent link, a channel, was floated for centuries, but the engineering challenges of tunneling under the sea were staggering. This wasn't just about length, but about working in a highly unstable geological layer, beneath a fluctuating seabed, constantly battling water ingress, all while ensuring two distinct nations could safely connect. The vital mechanism that made the Channel Tunnel possible was a specific geological layer, the lower chalk. This unique, impermeable rock stratum, a thick bed of chalk marl, runs consistently beneath the English Channel. It was firm enough to bore through, yet soft enough not to necessitate constant blasting, and crucially, impermeable enough to largely keep the sea out. 6 tunnel boring machines, 3 on the British side and 3 on the French, advanced through this layer. Each machine excavated a 21-foot diameter bore, lining it immediately with precast concrete segments to prevent collapse and water infiltration. The 3 parallel tunnels, 2 for trains and a central service tunnel, extend for 31.5 miles, with 23.5 miles of that beneath the seabed. Precision guidance systems, including GPS and laser technology, ensured that the British and French tunnels met almost perfectly in the middle, achieving a vertical alignment error of just 14 inches. Completed in 1994, the Channel Tunnel transformed European transport, making a previously impassable barrier a mere 35-minute journey. Number 4, the International Space Station. From the depths of the Earth to the edge of space, let's consider the ultimate megaproject, an orbital outpost, perpetually circling Earth at 17,500 miles per hour. This wasn't about building on land or under the sea, but assembling a structure in the vacuum of space, over 200 miles above the planet, relying on human ingenuity and robotic precision for its very construction. The challenge was not just getting materials into orbit, but connecting delicate modules, each the size of a bus, with absolute reliability, while simultaneously creating a habitable environment in the most inhospitable place imaginable. The fundamental trick of the International Space Station, or ISS, is modularity and robotic assembly. It wasn't launched as a single unit, but assembled piece by piece over 2 decades, starting in 1998. Each module, weighing up to 35,000 pounds, was launched individually on various rockets, then docked and attached using a combination of astronaut spacewalks and the station's robotic arm, Canadarm2. This 57-foot-long robotic arm, capable of moving objects weighing over 250,000 pounds, was critical for maneuvering the large modules into place and connecting utilities. The ISS relies on a complex network of power systems, including 8 enormous solar arrays covering an area of nearly an acre, generating up to 120 kilowatts of electricity. Its environmental control system meticulously recycles water and oxygen, creating a closed-loop life support system for its rotating crews. Circling 240 miles above Earth, the ISS represents an unprecedented feat of international collaboration and in-space construction, a floating laboratory that redefines our presence beyond Earth. Number 3, the Panama Canal Expansion. Journey back to Earth, to Central America, where the dream of connecting 2 vast oceans across a narrow isthmus became reality over a century ago. But even that monumental achievement needed to grow. The original Panama Canal, opened in 1914, relied on locks that could only accommodate ships up to a certain size, known as Panamax. The challenge of the expansion, completed in 2016, was to double the canal's capacity and allow passage for new Panamax vessels, ships so large they would have been unthinkable a century ago, measuring up to 1,200 feet long and 160 feet wide, carrying up to 14,000 TEUs, or 20-foot equivalent units of containers. The key to the Panama Canal expansion was not just bigger locks, but a revolutionary water-saving mechanism. The new Neo-Panamax locks, built parallel to the original system, are vast concrete chambers, each over 1,400 feet long and 180 feet wide. Unlike the old locks, which simply release water into the sea after each transit, the new locks incorporate 3 water-saving basins per chamber. These basins, essentially massive bathtubs, capture 60% of the water used in each lockage, allowing it to be reused for the next ship. This ingenious system saves millions of gallons of fresh water from Gatun Lake, a critical freshwater reservoir for both the canal and local communities. The construction involved excavating 150 million cubic meters of material and pouring 4.5 million cubic meters of concrete, fundamentally reshaping the geography of a nation to accommodate the evolving demands of global trade. Number 2, the Large Hadron Collider. Now, let's descend into the abstract, into a realm where the machines aren't about spanning distances or creating land, but about probing the very fabric of existence. Imagine a ring, 17 miles in circumference, buried 570 feet beneath the Franco-Swiss border. This is the Large Hadron Collider, the largest and most powerful particle accelerator ever built, designed to smash protons together at nearly the speed of light to recreate conditions just after the Big Bang. The challenge is not just accelerating particles, but bending them in a circle with incredible precision, holding them in a vacuum colder than deep space, and detecting the fleeting fragments of their collisions. The heart of the LHC's mechanism lies in its 9,600 superconducting magnets. These powerful electromagnets, cooled to an astonishing 1.9 Kelvin, minus 456 degrees Fahrenheit, colder than outer space, generate magnetic fields 100,000 times stronger than the Earth's. These fields are essential for guiding 2 beams of protons around the 17-mile ring, keeping them focused and steering them through thousands of turns. The protons are accelerated to 99.9999991% the speed of light, gaining energy with each circuit. When 2 such beams, traveling in opposite directions, are made to collide at specific points, their sheer energy transforms into new particles, revealing fundamental insights into the universe. The scale of the LHC isn't just physical, it's conceptual, pushing the boundaries of our understanding of matter and energy. Number 1, the Three Gorges Dam. Finally, we arrive at the most colossal human endeavor on our list, a single structure that has fundamentally altered a continent's geography and its future. Imagine a concrete barrier spanning the mighty Yangtze River in China, holding back a reservoir extending for 370 miles, longer than many countries. This wasn't just about generating power, it was about flood control for millions, improving navigation, and powering an entire nation. The challenge was containing the immense force of the Yangtze, creating the largest power station on Earth, and managing the environmental and social consequences of such a monumental undertaking. The staggering mechanism of the Three Gorges Dam is its integrated design for both power generation and flood control. The dam itself is a gravity dam, meaning its sheer mass of concrete, 28 million cubic meters, is what holds back the water. Standing 607 feet high and stretching 1.4 miles across, it impounds an astonishing 10.4 trillion gallons of water. Integral to its function are 32 main turbogenerators, each weighing 1,000 tons, housed within the dam. These enormous turbines harness the kinetic energy of the falling water, converting it into rotational energy that drives generators, producing an astonishing 22,500 megawatts of electricity, enough to power millions of homes. The dam's unique ship lift and 5-step ship locks allow vessels up to 3,000 tons to bypass the dam, while the vast reservoir provides a critical flood storage capacity, saving countless lives downstream. Completed in 2006, the Three Gorges Dam is not just an engineering marvel, it is a re-engineering of nature on a scale rarely contemplated, a true testament to human ambition and its profound impact. The bigger the machine,